This webcast discusses the energy of satellites. So all satellites have both potential and kinetic energy. They have kinetic energy because they are moving in either a circular or elliptical path around a central body. So by that movement they have kinetic energy. And then they also have gravitational potential energy because of their position in the gravitational field of the central body. So as a satellite gets closer to, for example, the Earth, its kinetic energy increases because it starts moving faster. And its potential energy decreases because it's falling closer to the Earth, right? I mean, just like if you lifted a ball up and let it drop to the ground, as it moves closer to the Earth, we consider that its gravitational potential energy is decreasing. Well, the same is for a satellite. As it moves closer to the central body, its gravitational potential energy decreases. And then the reverse happens as the satellite moves further away from the Earth. It begins to slow down, and so its kinetic energy decreases, but you can imagine it getting lifted higher above the planet, so it is moving further from that central body, and so its gravitational potential energy increases. The total energy of a satellite is constant, and that total energy equals the sum of the kinetic energy and the gravitational potential energy. This total energy is constant because the satellite and its central body comprise an isolated system. There are no external forces acting on this system, and so the energy remains constant. Regarding the gravitational potential energy, the zero reference point for a satellite's gravitational potential energy is different than for something that is close to the surface of the Earth. For a satellite, the reference point where potential energy is zero is when the distance between the satellite and its central body is infinity. So when they are infinitely far apart, the gravitational potential energy is zero. And then as the satellite comes closer to the central body, the potential energy decreases. What that means is that gravitational potential energy for a satellite is always negative. It's always a negative quantity. Let's look at how the kinetic energy of a satellite in circular orbit is found. So we're starting with an equation we're very familiar with. Kinetic energy is 1/2 of the mass of the object times its velocity squared. We know that the orbital speed of an object in a circular orbit equals the square root of gm over r. And so if we plug that speed into the kinetic energy equation, we get that the kinetic energy of the satellite equals the gravitational constant times the product of the masses of the satellite and the central body divided by 2 times the orbital radius. And that is the orbital radius, the distance between the center of the central body and the center of the satellite. Now the gravitational potential energy, we'll see how that's derived. We begin with an equation we're familiar with, that the gravitational potential energy equals the mass times acceleration due to gravity times the height. Well, we know acceleration due to gravity equals gm over r squared. So we're going to put that in for the g. And we know that gravitational forces are attractive. They pull things toward each other. And the gravitational potential energy is defined to be zero when the orbital radius equals infinity. As that orbital radius gets smaller and smaller, meaning as the satellite moves closer to the central body, the gravitational potential energy gets smaller, and that means it's becoming more negative. Remember, the gravitational potential energy of a satellite is always negative. The h is the distance of the satellite from the central body, and that is the orbital radius, which we call r. So we replace h with r. And when we put all that together, the gravitational potential energy of the satellite equals negative g times the product of the masses divided by r, the orbital radius. Now the total energy of the satellite is the sum of the kinetic energy and the gravitational potential energy, and when we add those two things together, we get a negative number. So the total energy of a satellite is always negative, and you can see that the magnitude of it is the same as the magnitude of the kinetic energy, but the sign is negative instead of positive. Okay, so here are those three equations summarized on a single page. And so because a satellite in circular orbit is moving at a constant speed, the kinetic energies and gravitational potential energies are constant values. They have the same kinetic energy and gravitational potential energy at every point in their orbit. Now, in elliptical orbits, the satellite's speed is continually changing as its distance from the central body is changing. So as it gets closer to perihelion, it speeds up. So when it is very close to the central body, it is moving quickly, but as it moves further away, it slows down and moves more slowly. But the total energy of a satellite in elliptical orbit is a constant value, and you can find it with this equation. The total energy equals negative g times the product of the masses divided by 2 times the semi-major axis. So if you compare this equation for the total energy in an elliptical orbit, you'll see that it's quite similar to the total energy of a circular orbit, but instead of using the orbital radius, we're using the semi-major axis as the description of the distance. Let's go work a few problems involving the energy of satellites. And so I'm going to our worksheet 7D, and let's just look at the first problem here, where we have a satellite launched to an orbit at an altitude of 700 kilometers above the Earth. They're giving us the mass and radius of the Earth, and it tells us to assume that the orbit is circular. Okay, so the first question is, what is the gravitational potential energy of the system comprising the Earth and the satellite? So we're looking for the gravitational potential energy, and that is always a negative number, and it equals the gravitational constant times the product of the masses divided by the orbital radius. And I'm just going to go back and check that I have the correct equation, but I do. I just wanted to double check before we plug numbers into here. Now we are going to need to find that orbital radius by adding the radius of the Earth plus the altitude, because that would give us the total distance from the center of the Earth to the center of the satellite. So that's going to be 6.38 e to the 6 meters, that's the radius of the Earth, plus the altitude is 700 kilometers, which is 700,000 meters. And so if we add those, we get that the orbital radius here is 7.08 times 10 to the 6th meters. Okay? So I think we have everything now. It's going to be negative g. The central body mass is 5.97 times 10 to the 24th kilograms. The mass of the satellite is 9,800 kilograms, and the orbital radius is that 7.08 e to the 6th meters. Okay? And so we get that the that the gravitational potential energy is negative 5.512 times 10 to the 11th joules. And it is negative. Okay, the kinetic energy of the satellite. Well, I know that the equation for the kinetic energy of a satellite, and it will be positive, is G times the product of the masses divided by 2R. Now, I could plug everything in again and calculate this, but I can tell by comparing these two formulas that it looks like the magnitude of the kinetic energy is 1/2 of the potential energy. So this is going to be 1/2 the absolute value of the potential energy. And so I'm going to just do it that way. And so I'm going to get 2.756 times 10 to the 11th joules. Okay, and then the total energy of the satellite is the sum of the kinetic energy plus the potential energy, and so that is going to be negative 2.756 times 10 to the 11th joules. Okay, let's look at the next problem, number 2, where we have a satellite in circular orbit with an altitude of 359 kilometers, but we want to move it to a much higher circular orbit with an altitude of 35,800 kilometers. So the initial orbital radius, and let me just write that out so that we're clear. Is the radius of the Earth plus 359,000 meters. Let's see. Which is 6.739 times 10 to the 6th meters. But the final orbital radius is much larger. And it is going to be the radius of the Earth plus 35,800 kilometers, which is 35,800,000 meters. Which gives us 4.248 times 10 to the 10 to the 7th meters. Okay, and the question is, what is the difference in energy between the two orbits? In other words, how much work will we have to do to accomplish this orbit change? How much energy do we have to add to the satellite? And so we're looking for the change in the energy of this satellite, and we're looking for the total energy, how the total energy changes. And so I want to take the total energy at the final situation minus the total energy at the beginning. Now, the total energy of a satellite with a circular orbit is negative G times the product of the masses divided by 2 times the orbital radius. So everything would be the same here except orbital radius, I would use the final one, and then minus a negative GMM over 2 times the initial orbital radius. There are quite a few things here that can be factored out. Look here. In fact, I can factor out the negative sign as well. And so I'm going to do that. So this equals, I'm just factoring out negative G times the product of the masses divided by 2. And then that's times 1 over the final orbital radius minus 1 over the initial orbital radius. Okay, so now I'm at a point where I can plug in here. So the mass of the Earth is 5.97 times 10 to the 24th kilograms. The mass of this satellite is 9,550 kilograms. And then I'm going to have 1 over the 4.248 e to the 7th meters minus the 1 over 6.739 e to the 6th meters. I don't usually do this. I usually like to calculate it all at once, but I want you to understand why this is going to take a positive amount of energy, even though I see that negative sign at the front. Okay, so all of the things that I've factored out here. So I've got the universal gravitational constant times the mass of the Earth times the mass of the satellite divided by 2. So this is negative 1.901 e to the 18th. But in the brackets here, I have 1 over the 4.28, or 4.248 e to the 7th, and I'm subtracting 1 over the 6.739 e to the 6th. And this is also a negative number. And so when I multiply these two things together, I'm going to get a positive because, the negatives cancel. And so the change in the energy, in other words, the work that is required to move the satellite to a higher orbit, is going to be a positive 2.374 times 10 to the 11th joules. It will always take a positive amount of energy. You have to add energy to move the satellite to a higher orbit.